So welcome you to today's lecture. Does anyone has any questions from the last lecture?
Sir, I have few doubts from the lecture number 19.
That was the last lecture you're talking about?
No, sir.
That is
The previous to that one.
estimation part, right?
Yes, sir.
So that maybe we can discuss it on Friday when we have a tutorial, right?
Okay, sir.
So we can discuss it on Friday because this Friday I don't have any new homework due. So we'll have a general discussion this Friday. We'll have more time to discuss general things. Or you can stay back after the lecture and we can then discuss it, right? That is also possible.
Okay, sir.
So I inquired with the lecture hall complex about the availability of rooms. So it looks like room is not a problem. The only problem is the recording part. They will not be able to provide recording, but what they have said is they have classrooms where cameras are already mounted. So what we can do is Friday, we can give a try because Friday is a tutorial. It's not a regular lecture. And this Friday, anyway, we don't have any new homework due. So we can have an experiment meeting in the lecture hall complex and see if it works fine for people who are not able to attend, especially those who are not on the campus. If they can, if they find that recording useful, then we can have a physical lectures in classroom. So let us try to meet on Friday on an experimental basis. And then let's see how things work. If we are recording, the quality of recording is good, and then the people who are not on campus are fine with it, then we'll meet physically from Monday onwards. Does that sound good?
Yes, sir.
Any objections to this arrangement, which is tentative right now? Okay, if there are no objections, I assume that the proposed arrangement suits everybody. So let us start with what we were doing in the last lecture. Last lecture, we started with the testing problem. We formulated the testing problems. We defined the concept of a test function because a typical testing problem is the one where you have to test a given hypothesis, which we call as null hypothesis, against an hypothesis which we call as an alternative hypothesis. So there are two possible actions available to you. One is reject H0, and the second is not reject H0. Now, since there are two possible actions, there are two possible errors which one may make while making decisions. One is wrongly rejecting H0, and the second is wrongly not rejecting H0. And then ideal thing would have been if I was able to minimize both kind of errors simultaneously. Then we saw that it's not possible to minimize both kind of errors simultaneously. If you try to minimize one, the other would increase. That is where the problem is. Just 1 second, let me just connect this call. सुप्रिया आयुष का फोन है Yeah, sorry for this interruption. There was a call which I was expecting, and then yeah. So yeah, what we realized was it is not possible to minimize both kind of errors simultaneously. So a common approach which is being used in testing problem is you try to put an error bound on one kind of error. So that is a type 1 error. We fix a upper bound on the type 1 error which we can afford. And then I try to minimize the second kind of error which we call as a type 2 error. Now, in such a situation, a natural question, a philosophical question which arises is, why to put a bound on type 1 error? You can put a bound on type 2 error itself, but there's no loss of generality in doing so. But then whatever error bound you are putting in one kind of errors, that error should be more serious than the other, because that is something which you don't want to compromise with. And that's the reason why you want to put an upper bound on it. So you can always frame your null hypothesis and alternative hypothesis in such a way that type 1 error is considered to be more serious than the type 2 error. Or in other words, wrongly rejecting H0 is considered to be more serious than wrongly not rejecting H0. Once you have done that, then putting an error bound on type 1 error makes sense, right? So one has to keep in mind that when we are putting an error bound on type 1 error, the understanding is the type 1 error is more serious than the type 2 error, because I'm not controlling the type 2 error, I'm just controlling the type 1 error. Then we saw that we also discussed that, look, while we are doing this, although I'm sure that type 1 error is bounded above, I don't have anything about type 2 error. So that means if your test concludes that reject H0, you would reject H0, right? Because the chances of wrongly rejecting H0 are less than or equal to alpha, which would be very small, 0.05 or so. So if your test concludes that reject H0, you can confidently reject H0 because the chances of wrongly rejecting H0 by your test procedure is very small, 0.05. But if your test does not say that do not reject H0, then you are in a tricky situation. Then you cannot take a decision immediately, because you cannot accept H0, because you do not know what is an error of that second kind of error. That may be very high, that error. So, and for that, it is important to study the power of the test. So this is what I did last time. And I did this example of normal theta 1. I saw that if I put an error bound as alpha, my C alpha turns out to be 1 upon root n, phi inverse 1 minus alpha. Your test procedure is phi alpha x is 1 if x bar is greater than C alpha, 0 if x bar is less than or equal to C alpha. So
sorry to interrupt. I have a doubt regarding this.
Yeah.
In this case, in this example, why are we considering the non-randomized test function, not randomized?
Yeah, good question. You can consider randomized. There is no issue with it, right? As we'll see, this is just an example. I'm not saying you can consider anything, right? But as we will see later on, in such a situation, your non-randomized is as good as the randomized one, right? So why to go for a, because Neyman-Pearson lemma, when we do, we'll see that Neyman-Pearson lemma tells us that it is enough to consider the non-randomized rule, at least in the normal example. Is that okay? But your question is valid. Your question is valid in the sense that you can always say that I can consider a non-randomized. So for example, let me just give an example. So let us try to think statistically. Statistically, if I start thinking, it says I have a sample from normal theta 1. All right. I have to test whether mean is less than 0 or mean is bigger than 0, right? So let's look at, if I apply my statistical mind, a representative of theta in the sample is sample is X bar, right? Because it's a population mean, so a sample mean looks like a good estimator, right? We have seen that with the UMUE effect, right? So the value of theta should somehow gets reflected in the value of X bar, which we observe, right? Now note that we are rejecting H0 if theta less than or equal to 0, right? We are rejecting H0 if theta is bigger than 0. That would get reflected here is whether X bar is bigger than 0 or not. But X bar may not be exactly 0 because there's a chance that although the mean may be 0, theta may be 0, but X bar may be 0.01, minus 0.01, and so on, right? So in this case, that is why I said a reasonable test procedure is I reject H0 if X bar is large, because it is under H1, large values of theta are there. So I reject H0 if X bar is large. So that could be one test. Another may say, look, I can also consider a test phi. I say that, look, because it is talking about theta is equal to 0, so I say I reject H0 if X bar is bigger than 1. Right? I reject H0 because there is a possibility that X bar or 0.5 is. Right? But if X bar is near 0, I'm not sure. So X bar is minus 0.5 to 0.5. That is where theta is 0, because then I know that theta could have fallen here or here. Then I do a randomization, right? I can say that if X bar happens over here, I reject H0 only with probability half. It could be gamma, in fact, in general, right? Anything. I'm just giving you an example of a randomized test which you're talking about. And if X bar is greater than or equal to 0.5, I reject H0 with probability 0. This also looks like a reasonable test procedure. But here I cannot fix alpha because I have to put a bound on alpha. So I put a gamma over here, right? And gamma is chosen so that my error bound is alpha, right? So if I have to do that, what is the expected value of phi in this case? Probability that X bar is greater than 0.5 plus gamma times probability that X bar lying between minus 0.5 to 0.5. And now you can choose gamma so that this quantity, supremum of this quantity is alpha, right? So you can consider randomized tests. Right now, I'm not talking about which test is better than the other. Right now, I'm just giving you an example that this is a test procedure, a best valid test procedure in this situation. Is that okay? Does that sound okay to you?
Yes, sir.
Okay. So what we saw in this case is this test has level alpha, but it can have a very bad power near theta is equal to 0. And which makes sense because theta is equal to 0, then it will be difficult to discriminate theta from anything theta slightly less than 0. Right? So it is expected that power near theta is equal to 0 should not be that good. And that is what is happening near theta is equal to 0. The power is 0.05. So type 2 error is 0.95, right? Power is 0.05, that means type 2 error is 0.95. So very high type 2 error. Now let's talk about the p-value of a test. It is the smallest possible level of significance at which H0 would be rejected for computed phi alpha x. So what happens is your test procedures is prescribed in advance. Now then, after you have taken a data, you see at what is the smallest level at which my test would have rejected H0 for the given observed value. Okay? That is called the p-value of the test. And p-value of the test is very important in the sense that you know that you observe this data, then somebody may ask, look, how comfortably you can reject H0. Okay? So if p-value turns out to be very low, then you say that no, I'm very comfortable that in rejecting H0. So it is the smallest level of significance at which you would have rejected H0 based on the given data, which you get X. So it is the smallest possible level of significance alpha hat at which H naught would be rejected for computed phi alpha x. So this is after the data has been taken. So alpha hat x, the p-value of test phi is alpha hat x is infimum over all alpha belonging to 0, 1, such that phi alpha x is 1. Right? So let us look at last example. Last example, even though alpha is, let us say, fixed, my test turns out to be reject H naught if x bar is greater than C alpha, 0 otherwise, where if I want my level to be less than or equal to alpha, C alpha is bigger than or equal to 1 upon root n, phi inverse of 1 minus alpha. Now, after I have observed sample, I have this x bar, sample mean. Now, suppose this sample mean is above this C star, which you already know. So what is the smallest level at which you had rejected H naught? Well, x bar, because your test is rejecting for a larger values. So what is this threshold? I would have rejected H naught even if this C alpha was same as x bar. So my P test becomes, what is the probability that x bar is bigger than this x observed? Let me call this as x observed. And I look at size would be supremum over H naught P of P. This is the smallest level at which I would have rejected H naught for this observed value of x bar. I try to see this. H naught is theta less than or equal to 0, so it is supremum theta less than or equal to 0. Probability x bar is greater than x observed. After standardization can be written as 1 minus phi of root n x bar minus theta. Root n is 5 because n I have taken as 25, so it is 1 minus phi x bar. Now you know what is the observed value of x bar. For example, it may happen that you observe x bar as, let us say, 0.25. Then this smallest level at which you would have rejected H naught is 1 minus 5 times 0.25, which is 1 minus 5 times 1.25. And this value you can get from the normal table. That will be the p-value of the test, or the smallest level of significance at which you would reject H naught. So having a knowledge of a p-value is always useful because it gives you an idea about how comfortable you were in rejecting H naught, if your decision was to reject H naught. Right?
Sir?
Yeah.
Sir, can you please explain once more the way how to find p-value?
You see, what happens is, let us take an example. So for example, let us look at, so for example, let us look at this test, right? This is a test, you know. What is its level? Level that we have seen is 0.05, right? Last example. Yes. This level is 0.05. So this test is determined in advance. You have not taken any data because your test has to be prescribed before your data has been taken, right? So otherwise you may get biased. Now, after seeing the data, you may get biased and you may change your test or decision procedure depending on what you have observed. So to get a reasonable test procedure, you should always declare what would be your rule to take a decision before data has been taken, so that you don't get biased after taking the data, right? So that is a one important thing which you must keep in statistics. For example, you must have heard a lot of memes about statistics, a lot of sayings about statistics, that you can prove anything through statistics, which is not correct, which is true only for people who are biased in using statistics. See, after you see your data, and then you say, no, I'll use this decision procedure to justify my this thing. For example, suppose there is a test procedure based on a mean and a median, two different test procedures. The mean doesn't suit to you, median doesn't suit to you, and after the data has been decided, you see whether median is suiting to you or mean is suiting to you. Right? So this test procedure has to be defined in advance before data has been taken. So you have to define what would be your rule to take a decision. So if your level is alpha, you say my rule is, look, you go to the field, collect the data, calculate the sample mean. If sample mean turns out to be bigger than 0.33, you reject H0. Otherwise, you don't reject H0, right? That is what you would do. So this is done in depth. But after that, suppose I have now concluded the test. I have taken the data. He would say, look, this 0.33 level, let us say if I observe my X bar to be what I had in 0.25. Right? Suppose X observed after the data has been taken, X observed was 0.25. Right? Then note that I would had, sorry, not 0.35, right? So that I reject H0 because 0.35 is bigger than 0.33. Now the question is, I am rejecting H0 because X bar is bigger than this. Note that I would have rejected H0 even if this threshold was 0.35. Right? Because my test procedure is of the type 1, if X bar is greater than C, and 0, otherwise. That is a right. You are rejecting. Now, C in this case is 0.33. Now, even if this C was 0.35, I would have rejected H0. Right? So my P value becomes supremum under H0 of probability regard, because it was for large values, X bar greater than 0.35. Is that okay? After I have taken the data, this is what my
So
observation.
if C would have been 0.35, then it would have lied in the otherwise part, no, sir? I mean,
C was
X bar greater than 0.35, if it would have been,
yeah.
Then if we have observed 0.35, then that would have lied in the 0 if X bar less than 0.35.
See, it is a continuous random variable.
Sorry. Yes, right.
So that
doesn't matter. Okay.
Right?
Yes.
So I'm saying if not 0.35, 0.35, 0.00001, right? Very near to 0.35. So this is what the P value would have been, right? Because even if with this, I would have rejected H0 with this value. So what is this quantity? This is supremum over theta naught, 1 minus phi of probability that X bar is less than or equal to 0.35, N was 25. So root N is 5. 0.35 minus theta, root N X bar minus, yeah. And this is an increasing function of theta. Under theta naught, theta is less than or equal to 0. So supremum would be at theta is equal to 0, so that equals 1 minus 5 times 5 into 0.35, which is 1 minus 5 times 1.75. You can calculate this value, that is the P value of the test. Is that clear?
Yes, sir. So this means that we must have the idea of the direction in which we would have the rejection.
No, that test, because test procedure is defined in the beginning.
Yes, that needs to be defined. And after that, we can calculate the P value.
P value, right? After data has been taken.
Yes, sir.
P value, because you see, test procedure is defined in the beginning. So you do not know what it is going to be. So your test procedure is like this. But after data has been taken, you observe that X bar is 0.35. That means I would have rejected. Now, this 0.33 is dependent on the level. This 0.33 has come with the level 0.05. Now, if I reduce this level, this 0.335 would increase. You see, if my level was 0.025, let us say, then in place of this 0.33, it would have been something else. Right? So the question is, I can keep on decreasing my level, but then this rejection region would become smaller and smaller, right? So the question is, after I have taken an observed value X bar 0.35, how much I would have played around with this 0.33? Even if my test procedure was 0.35, which gives me a level as this, I would have still rejected it. Right? So it only tells you how comfortable you are while rejecting H0.
Okay, sir.
Right?
Thank you, sir.
You see, for example, even in this case, let us look at my test procedure was this, right? I'm saying reject for larger values of this, and it depends on alpha, right? Can anyone calculate what is the phi of 1.75? Does anyone has a calculator, or can anyone tell me what would be phi of 1.75? Just see the Google calculator of normal CDF. Can anyone tell me? You can't find it out?
Sir, it would be 0.9599408.
How much 1 minus, how much 0 point?
9599408.
95? 008?
9599408.
9599. So let us say 96 around, right? 0.96 around. Which is 0.04, right? So note that if my threshold, this C, was 0.35, if this threshold was 0.35, the corresponding level would have been 0.04. So what it says is, I would have rejected H0 even at level 0.04, because for 0.05, I got the value 0.33. If my level was 0.04, I would have gotten this value as 0.35, which is my observed value, and I would have still rejected H0, right? So you see, now it says I'm more than 5% sure that I can reject H0. It's 0.04 because p value is turning out to be 0.04 for the observed data point. Is that clear too?
Yes, sir.
Yeah, okay, great. Now let's look at this example. With additional information provided by p-values, using p-values is typically more appropriate than using fixed level tests, because the test procedure can tell me the principle that you reject for large or small values. That tells me a rule. For how large, that would come with a rejection region, right? That p-value. So when you determine the p-value, determine if you reject H0 with this p-value, you know what is the kind of a error you are committing in rejecting H0. So in the example discussed above, the level of test phi c star is equal to size of the test. Why? Because it is a continuous case, and you saw that supremum over theta belonging to theta naught, right? You saw that this is theta. You considered C alpha is equal to 1 upon root phi inverse alpha, because you look at supremum, which was size, and you put that is equal to 1 minus alpha, right? That is the reason why size and level of the tests are same. Now, in general, size and level of the test may not be same, especially when we are talking about discrete distributions. Let us look at this example. X is binomial and 2 theta. Two possible values of theta are 1/2 and 1/4. I want to test theta is equal to half against, sorry, theta is equal to 1/4. Not a good test procedure. I should put theta is equal to 3/4 actually. That is a much better. H0 that theta is equal to half against theta is equal to 3/4. Now note that here alternative hypothesis theta is large because 0.75 is bigger than half. So a test procedure should be you reject for large values of number of successes or proportion of successes, right? Because expected value of X is n theta, which is 2 theta. So large values of theta get transmitted into large values of X. So reasonable test procedure would be one which rejects for large values of X. How large? You know that x, large value of x could be 0, 1, 2, or because x is discrete. So I consider test procedure 5jx. There are 3 different test procedures. One which rejects for large values as 0, one for large values as 1, one for larger values beyond 2. Let us look at what are the possible kind of labels I can have. What is a label? Label is expected by beta phi 0 x. So that is a this is not beta phi 0 x, this will be beta phi 0 theta. So beta phi 0 theta. Phi 0 theta means it rejects if x is greater than or equal to 0. So it is probability that x is greater than or equal to 0. And since x is a binomial, probability x greater than or equal to 0 is fine. Let's consider the test phi 1, which rejects if x is greater than or equal to 1. So what is a beta phi 1 theta, which is probability x greater than or equal to 1, which is same as 1 minus probability x equal to 0, which is 1 minus theta whole square. So if I consider the supremum over this, because that is what you have to consider, it can go as large as 3 by 4, right? Because the theta under h naught is half, so it can go to 3 by 4. So 1 minus 1 by 4, which is 3 by 4. Let's look at test phi 2. Phi 2 rejects for values larger than 2. So beta phi 2x theta is probability x greater than or equal to 2, which is same as probability x equal to 2, which is theta square. What is the supremum under theta naught you can have? 1 by 4. So you know that possible values of beta phi theta could be only 1, 3 by 4, or 1 by 4. So I can have a label same as size only when my label is either 1, 3 by 4, or 1 by 4. Right? Otherwise, I cannot have a label same as size. Okay? So the label is same as size only if my alpha is 1 by 4, 3 by 4, or 1. Otherwise, label would always be less than size. Otherwise, because label is something you want to put an upper bound. And what is a size? Size is the least upper bound of the, it is a supremum over beta phi theta. So label would always be less than or equal to size in general. So here, if you want to have a label same as size, the only values of alpha possible are 1, 3 by 4, or 1 by 4. So let's look at, can anyone tell what is the label alpha is equal to, let us say, 0.6. Yeah. If I want my level to be 0.6, or let us say level to be 0.05. Can you tell me what would be the test? So I want my beta phi naught, theta is half under h naught. Right? H naught there is only 1 point, so beta phi naught theta should be less than or equal to 0.05. Now note that my test procedure for phi 0, it is 1, which is bigger than or equal to 0.05. It cannot happen. 3 by 4, also it cannot happen. Phi 2 also, it is 1 by 4, which is bigger than 0.05. That cannot have. So none of these tests can be of label alpha. Now suppose my label was none of the tests, none of these tests, none of phi 0, phi 1, and phi 2 could be off. So in this case, the only label alpha test would be one which always reject h naught, for which beta phi naught theta would be 0, and 0 is less than or equal to 0.05. So the only test in this case, if your label wants to be 0.05, the only test which you can have is the trivial test which always reject h naught. Now suppose my label was 0.3. Now 0.3, then beta phi 1 is not less than or equal to 0.3. 3 by 4 is also less than or equal to 0.3. But 1 by 4 is less than or equal to 0.3. So the test would be beta phi 2 in this case. So in this case, your test is, you want beta, so your test would be always rejects H0. That means phi star x should always be 1 for MTX. So if you want level to be 0.05, the only test possible is the one which always rejects H0. XJ given equal to this thing, yeah. So no, phi stars would be 0, right? Which never rejects H0, because for that expected value of phi star x is 0, which is less than or equal to 0. So in this case, you see that it may not be possible to have size same as alpha. Size says as level, unless level is either 1, 1 by 4, 3 by 4, or 0. Now let's consider this example. X has binomial 2 theta, where theta is an unknown parameter. And let us consider n is 2. So my n is 2. Consider testing H0 that theta less than or equal to half against theta greater than half. So here again, under alternative, you have large values of theta. So you would reject, a reasonable test would be one which rejects for large values of x. So I consider this test, I reject with probability 1 if x is bigger than j. But if x is same as j, I do a randomization. And I reject only with probability gamma. And 0 if x is less than j. So this is an example of a randomized test, which says that if you observe x greater than j, there is no need of a randomization. You reject H0 with probability 1. If you observe x is less than j, then also no randomization is necessary. You do not reject H0. That is your decision. But in case if you observe x equal to j, then you do a randomization. You toss a coin whose probability of success is gamma, and probability of failure is 1 minus gamma. So if you observe x equal to j, you toss a coin, such a coin. If head turns up or a success turns up, you reject H0. Otherwise, you do not reject H0. That is what it means. So randomization is necessary only when x equal to j is observed. So there are 3 possible decision rules one can think of, or 3 possible test procedures one could think of, depending on what the value of this threshold j is. So j is -1, 0, 1, and 2. Because the possible values of x, you know, is 0, 1, 2. So it could be x greater than -1, which means it takes value 0, 1, 2, and so on. Suppose we want size to be same as alpha. Okay. Let us look at beta phi j theta, which is expected value of this quantity, which is probability that x greater than j plus gamma times probability x equal to j. Now one can easily see, because x corresponds to the number of successes, as theta becomes large, number of successes are expected to be large. So this probability is expected to be large, because then x is supposed to increase, right? If theta increases, x is supposed to increase. So that means this probability is expected to be large. So it can be shown that beta phi j nu theta is an increasing function of theta. So thus, supremum of this test would be at supremum over H0, and since that is an increasing function, the supremum would be attained at theta is equal to half. So which is this supremum over H0 would be beta phi j at half, which is probability at theta is equal to half of x greater than j plus gamma times probability under theta is equal to half of x equal to j. That is what I have done over here. Now, suppose I want my level to be 0.9 and I want my level to be same as the size. Let us look at if I take j to be -1. Then this quantity would be probability under theta is equal to half x greater than -1 plus gamma times probability x equal to -1 is 0. So this probability, which is 1. I go to the next level, next test, because I would see that whether I can reduce this further because I want my level to be 0.9. Then I go to the next test, which is corresponds to j is equal to 0, which is probability that theta is equal to half under x greater than 0. Probability x greater than 0 would be nothing but 1 minus 1 minus half whole square, which is theta 3/4. So if I just take gamma to be 0, right? Suppose if I take gamma to be 0, then this turns out to be this quantity. If gamma was 0. So I'm not playing around with the gamma right now. Probability theta is equal to, so I keep note that I want this probability to be 0.9. Right? So that means this quantity has to be smaller than 0.9. So I try to see what are the thresholds level j for which this value is less than 0.9. When I look at a threshold point -1, I see that this probability is 1. So I go to the next test, probability x greater than, because it is a decreasing function of j. As j decreases, it decreases. So I can keep on decreasing it by reducing j. So I go to the next level, probability x greater than half. Probability x greater than half, sorry, probability x greater than 1. Probability x greater than 1 is 1 minus 1 minus, just wait 1 second. So note that my test procedures are these. J is equal to -1, j is equal to 0, j is equal to 1, and j is equal to 2. Beta phi j gamma theta is probability x greater than j plus gamma times probability x equal to j. Supremum turns out to be at theta is equal to half, so this turns out to be this. I want this quantity to be 0.9. Right? I want this quantity to be 0.90. Now, if I want this to be 0.90, I know that this quantity is positive. So this plus positive quantity should be 0.9. So that means this quantity has to be less than 0.9 or at the best 0.9. So this quantity has to be less than or equal to 0.9. So I try to choose j such that this quantity is less than or equal to 0.9. This is a decreasing function of a j. So that means if you keep on increasing j, this would keep decreasing. So I start with j is equal to -1. J is equal to -1. This probability turns out to be 1, which is bigger than 0.9. So I go to the next level, which is j is equal to 0. So probability x greater than 0 is same as 1 minus probability x equal to 0. Probability x equal to 0 is 1 minus 1 half whole square by 3/4. Now 3/4 has fallen below 0.9. So this suggests that I should choose j to be 0, and then to achieve this, I use this gamma. So thus we take j is equal to 0, which gives me probability x greater than j, x greater than 0, so then 3/4 plus gamma times probability theta is equal to under theta is equal to half x equal to 0. Actually, this should be 0.90. Or I want, there are some type of, so I think calculations have been done with 0.95. So let me change this to 0.9. Let me change this also to 0.9. So it comes over here, it is 0.75. 0.75 has fallen below 0.95. So it looks like I should stop at j is equal to 0. So for j is equal to 0, I get probability x greater than j as 3/4 plus gamma times probability theta is equal to half x equal to 0. I want this to be 0.95. 0.95 is 0.75. 0.95 minus 0.75 is 0.2. Gamma times probability x equal to 0 is 1 minus half square. And that gives me gamma as 0.8. So in this case, size is same as alpha, which is same as 0.95. And what is the corresponding test? The one corresponding to j is equal to 0. So that means I reject with probability 1 if x is greater than j. X is greater than G means X is greater than 0, which is X equal to 1 or X equal to 2. And I reject H0 only with probability 0.8 if X equal to 0. So this is what your test procedure becomes. So in this case, note that the value 5 star X doesn't take the value 0. So that means you never outrightly not reject H0. Okay. If X is 1 and 2, you outrightly reject H0. But if you observe X equal to 0, then you toss a coin whose probability of head is 0.8. You toss such a coin. If head turns up, you reject H0. Otherwise, you do not reject H0. So let's talk about now uniformly most powerful tests. So consider testing H0 that F belongs to P0 against that F belongs to P1, where P0 and P1 are two disjoint family of PDFs, and their union, suppose, is P. Suppose alpha, which is between 0 and 1, be a given level of significance. Normally, as we have seen, that we don't take alpha to be 0 or alpha to be 1, because choice of alpha is equal to 0 will give you a, most of the time, trivial test, phi x equal to 0, right? Which is a no data test, and which is highly unreasonable test. Now, goal is to find a test function phi star for which level is alpha. That means supremum over F belonging to P0 of beta phi star F is less than or equal to alpha. So level of significance is alpha. And it should have a maximum power. So that means for any other test phi satisfying 1 whose level is alpha, the power of phi star, which is beta phi star F, would be greater than or equal to beta phi F for F belonging to P. Such a test phi star is called uniformly most powerful test at level of significance alpha. So what does it mean is uniformly most powerful test is a test. So uniformly most powerful test of level alpha is a test whose level is alpha. That means supremum over F belonging to P0 beta phi star F is less than or equal to alpha. And it has a maximum power among all the tests for which level is alpha. In other words, for any other test phi for which level is alpha, that means supremum over beta phi F is less than or equal to alpha, the power of phi star, which is beta phi star F, is bigger than or equal to beta phi F. And power happens when F belongs to P1. Because beta phi F or F belonging to P1 gives you a power of phi star. So this is what should happen. So our goal is to find a uniformly most powerful test. Notice we did the concept of a sufficiency, and then a natural question may arise. Can we use the test functions which are depending on observations only through sufficient statistic? And the answer is yes. Let us see why. Suppose that the statistic T is sufficient. So normally such a statistic is minimal sufficient. So suppose T is minimal sufficient. Suppose I'm given any test function phi. What I do is I construct another test function phi star, which is based on T. And what is this test function? Expected value of phi x given T. So whatever original test function was, that given T. Suddenly, for this to be a test function, because it is a probability, it has to be between 0 and 1. So suddenly, since phi is between 0 to 1, expected value of phi would also be between 0 to 1. So this certainly belongs to 0 to 1. No issues with that. The only thing is it a statistic? Because I should be able to use it. I will be able to use it only when it does not involve any unknown parameter. It should only depend on observations, the T. But since T is sufficient, conditional distribution of X given T does not depend on the unknown parameter F or unknown PDF. So this does not depend on F also. So it is a proper statistic. And it also lies between 0 to 1. So this is a proper test function. So clearly phi star depends on T alone. And by virtue of sufficiency of T does not depend on F. Thus phi star is a valid test function depending on sufficient statistic T alone. Also, let us look at beta phi star f, the power function of phi star. It is expected value of phi star t, which is same as expected value of phi x given t. But expected value of a conditional expectation is same as the expectation of the original random variable. So it becomes expected value of phi. But expected of phi is same as beta phi f. So what it suggests is, if you are given any test function which does not depend on sufficient statistic, I can find another test function which depends on a sufficient statistic and whose power function is same as the power function of the given test function. So that means you can find an equivalent test function depending on sufficient statistic. So what this discussion suggests is, it is enough to consider those tests which depend on observations only through sufficient statistic. So let me stop over here. I was thinking to finish this name and Pearson lemma today, but I think there were a couple of doubts, so that makes sense. So we'll do that tomorrow. Tomorrow I'll have an online lecture only. On an experimental basis, we'll see on Friday whether we can meet in the lecture hall. Have you gotten the schedule of your lectures? In which lecture hall, what lecture hall has been assigned to you?
No, sir.
Okay, so I'll let you know in the due course by tomorrow or so. And then Friday, we can try to meet in that lecture hall. If the camera works fine and recording is of good quality, then we can continue meeting physically. But tomorrow we'll meet online, only because it's going to be a regular lecture. So that's all from my side for today. If some of you have any questions, you may stay back. Others may just leave. Okay. If does anyone has any questions? I see Rosan over here, Somita over here. Any questions from any one of you? So it looks like these people logged in and then.
Hello?
Yeah.
Yes, sir. Sir, I am trying to leave.
Acha, okay. That's
Yes,
fine. Okay, great. Okay, then see you tomorrow.